Hey guys, Buildzoid here from Actually Hardcore Overclocking, and today we're going to be taking a look at the MEG X570 Ace motherboard from MSI. So this board is going to be going up against the Crosshair 8 Hero from Asus and the X570 Aorus Master from Gigabyte. So this is, this is a pretty high-end motherboard. Like, this falls into that category of motherboards where it's like these are all rather overkill for even like your 3950X. These are going to be quite expensive though, actually significantly less, significantly lower price points than what you actually pay for like the flagships. Like the flagships for X570 are insanely expensive. Let's start off with some of the noteworthy features around the board, and then we'll move on to the VRM and like memory stuffs as well.
Before that, this video is brought to you by the EVGA GTX 1660 XC Black video card. EVGA's GTX 1660 XC Black uses a fat heatsink to allow the card to run at lower noise levels for longer, capable of sinking more heat before the fan kicks in, and also has day one game-ready drivers for game launches. The 1660 XC Black is short and compact for installation to small form factor PC builds, but if you need one that isn't extra thick, it's also accompanied by a dual fan counterpart with a thinner heatsink for standard dual slot support. Learn more at the links in the description below.
So starting off with the rear I/O, we've got a clear CMOS here, which I'm a huge fan of because this does make it possible to clear the BIOS. Super convenient if you're just overclocking your daily system and you get it into that scenario where it doesn't want to automatically recover. Though most motherboards these days are pretty good about recovering on their own. Anyway, below that we get BIOS flashback to actually be able to update the BIOS of the CPU. I mean, of the motherboard, without having a compatible CPU for the motherboard, because it does allow you to just update the BIOS without even a CPU installed. You just need to power the motherboard, which I think for MSI boards, the requirement is that you have the 8-pin and the 24-pin plugged in. And then there's like a bunch of requirements for the format of the USB stick and the name of the BIOS file on that USB stick and which USB port you plug it into. Then you whack this button and it'll update the BIOS for you. So yeah, pretty neat feature to have. And it is actually, like, as far as I know, every X570 motherboard that's coming out will have this feature. So, yeah, but still, kind of definitely nice to have. The Wi-Fi card is missing from the board. That will be present when you buy it retail. I assume it's been removed for the purpose of making this picture. Then you got 1 gig Intel LAN and 2.5 gig Realtek. Which I think that's the order the ports are in, and they might be swapped around. It doesn't really matter that much. You can check on MSI's website which one's which, right? And then that sort of covers everything in the rear I/O. We, of course, have the optional and very useful, extremely useful extra 8-pin. So, yeah, you don't need to plug this in. If you have a PSU that only has a single 8-pin power connector, you don't need to worry about the existence of this extra power connector over here. It doesn't do anything. Like, first of all, it's literally connected in parallel with the other one, so the motherboard can't distinguish between, like, can't tell the difference between this one being plugged in or that one. And the other thing is yeah, you don't need this. Like, you really don't need this, because the thing is, the first 8-pin can handle already up to 384 watts, and this is a problem if you're on some of the, like, Intel HEDT platforms can exceed that. 3950X... unfortunately, still can't, okay? Unless you're pushing a 3950X on, like, liquid nitrogen, you are not going to be exceeding that 384 watts power consumption figure. So the extra 8-pin is just completely useless for any kind of water-cooled overclocking for any Ryzen CPU that you can install within this motherboard. It doesn't do anything, so... yeah, it's just a thing that board vendors do for no reason, is add extra power connectors, because I guess it makes the motherboard look more impressive to people who don't know anything about how power connectors work, which is that, if the power connector, if you're not pulling more power than the connector's rated for, you don't need another one. So otherwise, the power connector would be rated lower. So anyway, moving on from the very useful, very useless extra 8-pin, we have the far more useful postcode readout right here. So you can tell a lot from the postcode, but it also depends kind of on the platform. On some motherboards, on some platforms, the postcode is completely useless. You might as well just have the four troubleshooting LEDs right here, which these will tell you if you have like a memory error, CPU error, VGA error, or a boot media error. And the postcode will tell you that too, but it'll generally give you more details. It's just that on some platforms, there's no extra details even through the postcode because it'll always end up on the same, like any memory issue ends up with the same final memory postcode, right? Or that kind of thing. So yeah, still definitely not, this is definitely a feature I really like to have on a lot of motherboards because when it does work, it can be super helpful and massively simplify the overclocking process. Now, the only complaint I have for this postcode right here is that it is located under the PCIe slots. It's not, luckily it's not like jammed somewhere right here where if you put another PCIe card, you're just never going to see it because it's going to be covered up. But if you were running two-way GPUs, I mean, that's not a very straight line. Well, yeah, the backplate of a GPU would start obscuring that. And then depending on how tall your other GPU is, yeah, you might not be able to see that postcode. The other thing worth noting here is that you do only get 4 SATA ports. I have no idea why there's only 4 SATA ports. It kind of looks like MSI just ran out of space on this board, but in that case, you know what? They could have just removed the OC dial, taken the postcode, moved that down here, which, like, I still don't like the postcode being located anywhere on, like, the lower half of the motherboard because of the whole GPUs are going to cover it up. Like, at least it's there, right? Like, at least there's a postcode. I will always having a postcode is better than not having one, even if it's in the wrong place. As long as you're not using too many GPUs. Because if you do use enough GPUs and it's covered up, then, you know, it might as well not be there because you can't see it anyway. But still, this thing right here, my personal experience with it is that it gives you overclock. So this is basically a bunch of overclocking profiles for your CPU. And the thing about CPU overclocking is that it's very simple. You raise the core voltage, you raise the core clock, and you check that you're not overheating or that you're not exceeding the maximum safe core voltage. That's all you have to do to CPU overclock. So I'd argue this, like, if this worked well, I'd argue it's still not very helpful. And the reality of it is that my experience with the OC dial is that the profiles on it generally range from very low clock speeds at extremely high voltage to even higher voltages and higher clock speeds. So it is not, like, I would never advise anybody to actually use this. Because the way this is tuned is that it's set up so that the profiles just work. And to achieve that, they basically just tend to just slam voltage into them. So, you know, that's kind of the thing is just, yeah, they're not good profiles whatsoever. This honestly, like, they should have replaced that with Sata Ports. Sata Ports are more useful than the OC dial. Anyway, next to that, we find a reset button and a power button. Those are, of course, extremely useful if you do have the motherboard on an open-air test bench. And that pretty much covers all of the overclocking features on this motherboard. So we don't get, like, dual BIOS switches or any kind of, like, super, like, extreme overclocking targeted functionality on this board. But we do get sort of the bare minimum for, you know, good overclocking, I would say, good overclocking support for, like, test bench usage. So anyway, moving on, the VRM. And in the VRM department, we have what would, like, a year, well, actually, it's not even like a year ago. If we go back a couple months, this would be an extremely high-end VRM. And it doesn't really change the fact that it is still an extremely high-end VRM. It's just not quite as extremely high-end as it used to be. Because we've got a V-core that is 12 phases. Bam. And then we've got +2, so 2 more phases on the SoC VRM over here. And the way this is controlled is with an international rectifier IR35201, which is, of course, you know, like this chip is everywhere because this is the default high-end voltage controller for high-end motherboards for the last several years. If you have a high-end motherboard, it probably has an IR35201, and if it doesn't have an IR35201, then it has an ISL169138, because those are literally the only 2 options available for CPU power for a very long time now. Well, there are some other options. They're just not as high-end as these 2 that I just listed off. Now, the one downside to the IR35201, and it's only really a downside now because there's an option which has more phases, is the fact that it only goes up to 8 phases. So here it's configured as a 6+2, and to achieve the 12 phases, MSI is using a whole bunch of doublers located on the back of the board. So on the back of the board, we have a bunch of these chips. And these are, of course, just a bunch of international rectifier IR3599s. And these are doublers and quadruplers, but they do not actively current balance themselves. So that actually falls entirely upon the voltage controller on the motherboard. So I've been digging through some international rectifier documentation recently, and it's come to my attention that technically the IR35201, because of how accurate its current sensing system is, it can actually current balance even through an IR3599. So there's a lot of other doublers out there which will actually integrate current balancing functionality, because if you use a doubler, you basically run into, with most voltage controllers, you would run into the issue of the controller has 8 current sensing inputs, and now you have 2 phases on one current sensing input, and it won't be able to distinguish which phase is which. But the 35201 is so good that it can still distinguish between which phase is turning on and off, because the current flowing through each phase, it's not DC, like it's not a fixed amount of current, it goes up and down. So it can actually tell which phase is which, and it can still current balance to some extent even through the 3599. So yeah, it's not like, so that's a mistake that there's in a bunch of my past videos. So yeah, this is actually like a 12 phase with current balancing. Because you can't current balance through the 3599s if your voltage controller is good enough to support that functionality, which not all are capable of doing. So anyway, the other thing worth noting about the doublers is that they do add a little bit of delay to your PWM signals, because they are an extra chip on your PWM line, and that does mean that you're going to have worse transient response than if you just kind of threw the doublers out and kept the same motherboard design overall. But the thing is, there's a lot of things you can do to your motherboard in terms of how it's designed to optimize the transient response that don't necessarily include throwing out the doublers. So I personally, my personal view on the doublers is, at least currently, because I'm still doing some I'm still researching more into how much impact the doublers actually have on transient response in real world usage, which I currently have a few tests that seem to indicate that, quite frankly, under certain loading conditions, it doesn't matter what you do, the VRM is just not going to have a chance. Under other loading conditions, that does make a difference, but yeah, so inconclusive test results so far, and my current outlook on it is that the difference seems to be so marginal that it doesn't really matter anyway. So yeah, I see no issues with using I see no reason to consider a VRM inferior just because it uses doublers compared to a VRM that doesn't use doublers. Of course, there is the XDP E132G5C from Infineon that now supports all the way up to 16 phases. Even then, the difference would be really marginal. With VRMs, a lot of the time you get into a situation where it's just like, well, there's technically a way to do this better, but it's not going to give you any return in terms of actual real-world benefits. So yeah, I really don't see a problem with MSI using the IR3599s, though it is technically an inferior control scheme to having, you know, an XDP E132G5C, and it is an alternative control scheme to just not using doublers at all, because there's upsides and downsides to not using doublers at all as well. So yeah, that's not like having a lower phase count is what I meant by that. Like if you had a 6 phase with no doublers, there's upsides and downsides to that as well. So we're not going to get into all of that. Anyway, for the actual power stages, MSI is using International Rectifier IR3555s, which are basically the standard high-end power stage for the last several years, except for the fact that last year we started seeing a whole bunch of smart power stages, which unfortunately just do everything that the POW IR stages do. They just do it better. They're more efficient, they have better current monitoring, they have better temperature monitoring, and they also integrate a bunch of safety functionalities that the POW IR stages don't integrate whatsoever. But nonetheless, these are still extremely powerful and efficient. So even though they have, like, you know, the minor downsides to these compared to smart power stages are honestly, like, unless you're a server, like the whole point of smart power stages is that they're meant for server applications, because their, you know, efficiency is absolutely the most important thing ever. So having a very accurate current monitoring system built into your power stage is super, is a priority. For desktop systems like this, yeah, it's not really. So the fact that this has slightly inferior current sensing is just irrelevant, and having the various safety features is also irrelevant when your VRM is this freaking overkill, right? 12 phases of 60 amp power stages, this has a theoretical maximum current throughput of 720 amps. you're not going to overload this anytime soon. So for the VRM running at 1.2, for the VRM outputting 1.2 volts at 400 kilohertz switching frequency on the actual phases, so that would be 800 kilohertz switching frequency at the controller, and then 5 volts drive. The efficiency of this VRM is as follows. So 100 amps output, which is where you'd be looking at for like slightly above 100 amps is basically all of the different 8-core CPUs, from the 7 nanometer 8-core to the 12 nanometer 8-core to the 14 nanometer 8-core. The 12 nanometer 8-core is actually by far the most power-hungry 8-core CPU on the AM4 socket, because it's basically the 14 nanometer chip, just with more leakage and higher clock speeds. So yeah, anyway, 100 amps output, this VRM will be producing about 11 watts of heat. It will not need a VRM heatsink whatsoever for that, right? Like, that's non-issue for a VRM, especially when it's a 12-phase. Like, it has so much surface area just because of how many components there are that you don't need a heatsink for 100 amps output whatsoever. Now, for 150 amps output, which is far more than any of the first-gen or second-gen Ryzen CPUs would pull safely. So you could actually get a 2700X to pull this current. It's just that after a few months of pulling that much current, your 2700X would clock significantly worse than when you first set up your overclock. So yeah, this would degrade a 2700X pretty quickly. But the 12-core Ryzen CPU, the new 7 nanometer one, that one will be actually capable of hitting this kind of current draw on safe voltages under extreme load. So we're talking like Prime 95 with, you know, a maxed out overclock. 150 amps output would be actually what the CPU would pull. And then at that kind of current output, this VRM will produce 15 watts of heat. Oh, yeah, 15 watts of heat, which means you still don't need a heatsink. Going up from 150 amps to 200 amps, which is where the 16-core Ryzen 3000 series chip will max out. So the 3950X. That one will max out around 200 amps. So again, like maximum voltage that you can run on like water cooling under a AVX workload, like say Prime 95 or video encoding or some really heavy CPU workload, you're going to be looking at maximum current draw sustained around 200 amps. And you're going to be, and the VRM is going to be producing about 19 watts of heat, which again, because this is a 12 phase, it should still be capable of dissipating this without needing a heatsink, though at this point a heatsink might be advisable. As that is a pretty significant amount of heat, and it also depends on like the airflow situation. Now, going up into the sort of theoretical current outputs for this VRM, so you know 300 amps, because it 60 amp power stages, right? Like who doesn't want to know what would happen if you actually made use of all the current capability that MSI offers on this motherboard? So if there were like, which on liquid nitrogen you can actually hit like 300 to 400 amps current draw, that is possible, but yeah, on water cooling or air cooling, you're going to be stuck at most. You're going to be stuck under that 200 amp range, where this VRM is absolutely ridiculous overkill. So anyway, 300 amps, you're going to be looking at about 30 watts of heat. At this point, the VRM heatsink is pretty much a necessity. 400 amps output, you're going to be looking at about 48 watts of heat. And you can technically design passive heat sinks for like all the way up to 95 watts of heat, right? There's passive CPU coolers for 95 watt TDP CPUs. The thing is just like designing those kinds of heat sinks tend to make them very bulky and kind of ugly, because you actually need to prioritize surface area and thermal efficiency over aesthetics. And so with the types of heat sinks that most motherboards come with, 48 watts of heat, you actually would need a fan to dissipate it. You wouldn't be able to do it passively if you follow like typical motherboard heatsink design these days. But if you had a heatsink that was actually designed to dissipate, like prioritized, you know, dealing with 48 watts of heat passively, it's doable. It would just kind of be rather bulky and pretty ugly. 500 amps output, this VRM would be producing about 72 watts of heat. That is still doable with a passive heatsink. It would just be very, very large at that point. And the preferred cooling method for that kind of heat output would, of course, be a water block. But as I said earlier, a Ryzen, even a 16-core 3950X, you're going to be looking at less than 200 amps of current draw. So yeah, this VRM for like an air-cooled or water-cooled build daily system, VRM is like V-Core VRM is total overkill. Yeah, you know, it's on par with the other options that you get at this price point. Honestly, within a given price range, you're going to end up with roughly the same solution for the VRM and the feature set and the memory and everything. So yeah, this is a solid motherboard. It's just that at this price point, in the price range where this motherboard is, I'd say all of the motherboards are pretty damn solid. So it's just like, yeah, you know, pick your own poison at that point. So SoC VRM, two-phase, more 55 power, 60 amp power stages. So not even worth discussing how much heat this is going to be putting out, because the SoC VRM never really needs to put out anything more than 20 amps. And quite frankly, a single 3555 can deal with that all on its own. That's not an issue. That's actually within peak efficiency for a single 3555. Yeah, SoC VRM is just totally overkill as well. And now let's move on to the memory VRM. So the memory VRM is this right here. At least the main one. There's a ton of supporting voltages like VTT DDR, which is done with just a linear regulator, and there's, well, no point listing them off. There's also like VPP, which is normally done with a small buck converter. Anyway, so VDDR, which is the big one, the most important one, that's just a single phase, but it is actually, like, out of the single phase memory VRMs, this one's one of the far more powerful ones, because MSI is using these, like, they've recently picked up a bunch of these MOSFETs, which I'm a huge fan of, because they're evidently cheap, because they use them everywhere, even on like low-end motherboards, but these are actually really good MOSFETs. So you have 4C029Ns from, well, not really good MOSFETs, but compared to what other cheap MOSFETs are, these are really good, as far as cheap MOSFETs go. But 4C029Ns from On Semiconductor for the high side, and then 4C024Ns for the low side, which actually makes this one of the more efficient single-phase memory VRMs out there. Not that that really matters. DDR4 really doesn't pull that much power. The most important thing for DDR4 overclocking is what's going on between the CPU socket and the memory slots. So all of this right here, which MSI has kindly highlighted for us with these visual indicators of where the, like, memory things here, non-memory things there, right? That's what that stripe is indicating. It's not actually electrically much of anything, because it is just a break in the solder mask, and you can see that it ends like right there. So it's just a break in the solder mask. Unlike the audio section isolation slot, it doesn't even go all the way through the board. So if we go on the back of the board, right, and we go to the, well, if we look in the memory section, you can't see that stripe anywhere here, but you can see it right here, because the thing is, here with the audio isolation one, you can actually shine a light straight through that stripe right there, because it does actually cut through every single one of the planes in the motherboard. The idea being that you basically isolate the audio section's ground plane from the ground plane of the rest of the motherboard, because obviously there's all kinds of things sinking current into the ground plane, so you're going to have all currents flowing in all kinds of directions on the ground plane of the main motherboard, and that would potentially lead to interference issues with the audio sections, right? If you had like return current from a PCIe slot flowing through your audio section, that would kind of suck. So that's the idea behind having the isolation slot. But the memory, you don't want to do that, because you actually want a solid ground plane in this area. Now, other interesting things that MSI is doing with the memory section here, which the visual indication doesn't actually electrically achieve anything. It's just kind of like, hey, this is where our memory stuff is. But what they are doing that's kind of interesting is that MSI is going for full ground fills over all of the memory traces, which seems to be like, I assume they're trying to do some kind of memory shielding with that. And I say assume that they're trying to do that because most motherboards don't bother with anything like this. Most motherboards, you can see all of the memory traces. Even motherboards that are really, really good at memory overclocking, you can still see all of the memory traces, but here, or at least most of the memory traces. But here, MSI has actually dedicated the very bottom layer and the top layer of the motherboard to basically just ground. Like this is just a great big ground fill all over where all of your memory traces run. And then they have another one down here. We can kind of see some of the power planes also being like, there's a power plane down here, which I assume is VPP. And then there's a VDDR power plane that should be running through here, but I'm not sure we can see it from this side of the motherboard anyway. So yeah, but they are doing the ground shields on the back of the board. They're also doing them on the front of the board, right? You can just, well, I mean, you can't see any memory traces, so that's how you know that they filled out the, did a ground fill all over the memory traces right here. And you can kind of see that the part of the ground fill over there. We have a little VDDR island over here because there's a power plane that goes like that, basically. Yeah, yeah, so MSI has obviously put some extra effort into the memory section of this motherboard. The topology that's actually hiding under all of this shielding is just a regular, well, MSI's daisy chain, because the thing is, like, not all daisy chains are equal. Okay, it also depends also how the BIOS handles how the BIOS handles the memory, but yeah, MSI has been doing daisy chains for ages and ages and ages. I'd say their daisy chains are really, really good at this point. It gives you the best, sort of the best of both worlds, where you can have a lot of RAM, or you can have very high memory frequency if you just use this DIMM slot and that DIMM slot. And also, if you're wondering, like, how much of a downside is there to daisy chain when you're populating all of the memory slots? Well, on X470, MSI's daisy chain motherboards would actually go from, like, so on like 2 sticks, you would easily do 3600 megahertz. On 4 sticks, you would generally top out around 3200, which that I would mostly say is down to the Ryzen Ryzen 2nd gen memory controller, more so than the actual memory topology, because MSI also uses daisy chain on Z390, and on Z390 that daisy chain is capable of hitting in excess of 4000 megahertz on 4 DIMM memory configurations. Just depends on the CPU quality and the actual specific motherboard, but they do have a few boards that with a daisy chain can go over 4000 megahertz on 4 DIMMs. So yeah, like, you know, this should not restrict you until you're trying to exceed 4000 megahertz, assuming that the CPU's memory controller is good enough. All of the big aluminum polymer through-hole bulk capacitors that we see around this motherboard are made by Nippon Chemicon, which is, as the name implies, a Japanese capacitor maker. These capacitors are all rated for 5000 hours at 105 degrees. Which doesn't sound like a lot, but that rating also includes full voltage, which these are 6.3 volt capacitors on your V-core, which V-core you're not going to be going over 2 volts. So that means the capacitors degrade slower. Also, the lifespan of the capacitor basically doubles for every 10 degrees that you reduce the temperature by. So 5000 hours at 105 degrees is like 10,000 hours at 95 degrees, right? So, yeah, like... and also, it's worth noting that aluminum polymers don't do catastrophic failures. They basically get slightly worse at being capacitors over time. So it's really like, this is fine. Okay, this is completely fine to use 5000 hours, 105 degree rated capacitors. There's as far as I'm concerned, if you're like, especially if your VRM is this overkill and you have a VRM heatsink on the motherboard, right? It comes with one. Then yeah, I don't see a reason to have like a 10,000 or a 12,000 hours rated capacitor, because the VRM is not going to be getting that hot that you would actually be concerned about the lifespan of the capacitor in the first place, right? That is it for the MEG X570 Ace. It's definitely like hardware wise, I really like the board. It kind of gives me Z390 Dark vibes with the trim that they have going on, but admittedly, like, this is just missing missing solder mask. It doesn't functionally achieve anything. It just kind of looks, it just gives you Z390 Dark vibes, but it doesn't do the same thing that like the gold trim on a Z390 Dark actually achieves. This board is competitive with everything else. The main downside I can see with this motherboard is the 4 SATA ports. Like, I really don't know why there's only 4 of them here. But other than that, there's really nothing else I can complain about. That at least like that I want to complain about. This is a really solid board. And the only question I have is just how does it compare in terms of memory overclocking to a lot of the other motherboards, right? Because like, it's nice to know what topology they have, and we can clearly see MSI is trying to do something with the memory layout here that's new, because on their past boards they wouldn't have these ground, like, actually I don't think they've done these ground fills over their memory traces on any other boards in the past, so that's definitely new. But I can't eyeball, you know, memory overclocking capability from just looking at the motherboard. So, and yeah, so that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support Gamers Nexus, we've got a Patreon. And there's also the Gamers Nexus merch store, which is store.gamersnexus.net, if you'd like to pick up things like mod mats. And then I have a channel called Actually Hardcore Overclocking, where I do more overclocking related stuff. So if you'd like to check that out, that would be awesome. There's going to be links to all of those things down in the description as well as in the comment section. So that's it for the video. Thanks for watching, and goodbye.